After 46 years of traveling through space, Voyager 1 finally sent back data from beyond our solar system that nobody saw coming. This isn't just another space mission update, it's a complete game changer for everything we thought we knew about the universe. The tiny spacecraft has crossed into interstellar space and discovered an environment so strange and structured that scientists are, honestly, rewriting their textbooks. Get ready to have your mind blown by what's really lurking in the darkness between stars, because the truth is absolutely incredible.
The Great Silence and Revival.
Space exploration hit a terrifying moment in late 2023 when humanity's most distant messenger went completely silent. Voyager 1, our faithful explorer that had been sending data for nearly 5 decades, suddenly started transmitting nothing but garbled, meaningless signals. Engineers at NASA faced an unprecedented challenge, performing brain surgery on a spacecraft using 1970s technology from 15 billion miles away. The culprit was a corrupted memory chip, likely destroyed by the same cosmic rays Voyager was studying. The fix required rerouting decades-old code into backup systems while dealing with a 22-hour communication delay. By April 2024, the impossible happened. Voyager came back to life, and what it began transmitting would change our understanding of space forever.
The Magnetic Revelation.
Something extraordinary happened when Voyager's magnetometer came back online. It revealed that space between stars operates by completely different rules. The spacecraft detected an interstellar magnetic field that's dramatically misaligned with our sun's magnetic influence, suggesting Voyager has encountered a galactic-scale boundary zone. These aren't minor variations. They're fundamental structural differences that point to magnetic turbulence zones where galactic fields twist and reconnect in ways scientists never predicted. The readings indicate Voyager might be navigating through invisible cosmic highways where magnetic forces create pathways and barriers throughout our galaxy. This discovery means the Milky Way has an underlying magnetic skeleton that influences everything from star formation to the flow of cosmic material, and we're only now getting our first direct measurements of this hidden architecture.
The Cosmic Storm.
The moment Voyager 1 crossed the heliopause in 2012, it encountered a radiation environment so intense it would be lethal to any human traveler. High-energy cosmic rays, accelerated to nearly light speed by distant supernovae and black holes, bombard the spacecraft at rates dramatically higher than anything measured inside our solar system. The jump wasn't gradual, it was like stepping through an invisible force field into a cosmic shooting gallery. These measurements reveal that our sun's protective bubble shields Earth far more effectively than anyone realized, creating a cosmic oasis in what's essentially a galaxy-wide radiation storm. The pattern of these particles isn't random either. Voyager has detected systematic variations suggesting natural radiation corridors that could represent the aftermath of ancient stellar explosions that shaped our galactic neighborhood millions of years ago.
The Whispering Void.
Forget everything you've heard about the silence of space. Voyager 1 has discovered that interstellar space is actually humming with constant activity. The spacecraft's plasma wave instrument detects persistent low-frequency oscillations that create a cosmic soundtrack most people will never hear. These aren't just random noise. They're organized pressure waves moving through space like invisible weather fronts. Multiple density spikes indicate Voyager is encountering shock fronts left behind by ancient supernovae that exploded thousands of years ago, with their energy still rippling through the cosmic medium. The most fascinating discovery is how layered this environment appears to be. Some regions are hotter, others denser, creating distinct climate zones in what we assumed was uniform emptiness. This cosmic weather system suggests interstellar space has its own complex meteorology.
Mapping the Invisible Galaxy.
Every data packet Voyager 1 transmits is helping scientists construct something unprecedented, a three-dimensional navigation map of interstellar space. The spacecraft has become humanity's anchor point for understanding the Milky Way's invisible infrastructure, measuring cosmic ray gradients, particle densities, and magnetic field orientations that reveal the hidden structure of our galactic neighborhood. This isn't theoretical modeling anymore, it's real-world cartography of the cosmos, like having a weather satellite for space between stars. The radiation mapping has profound implications for future human space exploration, as the intensity of interstellar radiation is far more dangerous than what astronauts encounter in Earth orbit. Understanding where natural shields and danger zones exist could determine whether humans can ever safely venture beyond our solar system, making Voyager's measurements crucial for planning humanity's next giant leap into deep space.
The cloudlet highway.
Since entering interstellar space, Voyager 1 has passed through at least 2 distinct interstellar cloudlets, regions where plasma, dust and gas density suddenly changes by factors of 2 to 3 times. These discoveries reveal that the space between stars resembles an ocean with currents, eddies, and weather patterns, rather than the uniform void astronomers once imagined. The probe's instruments show evidence of structured plasma ripples with clear boundaries and characteristics, suggesting large-scale organization in what scientists thought was chaos. NASA researchers now believe our sun is moving through the local interstellar cloud, with Voyager helping define its outer edges inside the much larger local bubble, an enormous cavity created by ancient supernovae explosions. These density shifts could affect Earth's exposure to cosmic radiation over millennia, as our solar system drifts through different interstellar environments, potentially influencing everything from cloud formation to biological mutation rates.
The galactic boundary zone.
So the transition from our solar system to interstellar space turned out to be, well, far messier and more complex than anyone predicted. Voyager 1 revealed that crossing the heliopause isn't like passing through a clean boundary. It's more like navigating a chaotic swirl of plasma, radiation, and magnetic forces that shift and change as our sun moves through the galaxy at 450,000 miles per hour. The boundaries Voyager crosses aren't fixed structures but dynamic zones that evolve constantly. Magnetic fields don't align as expected, radiation environments change dramatically over short distances, and plasma waves suggest ongoing activity that scientists are only beginning to understand. This complex interstellar weather creates an environment where the edge of our solar system becomes less of an edge and more of a turbulent frontier zone, where solar and galactic influences battle for dominance in an invisible cosmic wrestling match.
The ancient supernova trail.
The systematic patterns Voyager 1 detects in cosmic ray intensity and plasma density aren't just random fluctuations, they're actually geological records of our galaxy's violent past, written into the very fabric of space itself. The spacecraft appears to be following trails left behind by supernova explosions that happened millions of years ago, with their shockwaves still carving out pathways through the interstellar medium. These cosmic highways, you could say, channel high-energy particles along preferred routes, and that's what creates the radiation gradients and magnetic field orientations Voyager measures. Some astrophysicists even believe these ancient stellar explosion patterns might influence where new stars form in our part of the galaxy, with magnetic field orientations potentially guiding cosmic material into denser regions that could trigger future star birth. So, the data suggests Voyager isn't just sampling local conditions, it's really giving us a glimpse into the aftermath of cataclysmic events that shape the structure of our entire galactic neighborhood over, well, cosmic timescales.
The Eternal Ambassador.
While Voyager 1's scientific mission might end within a few years as its power source slowly fades, the spacecraft's journey through eternity is actually just beginning. This small probe will keep silently coasting through the cosmos long after human civilization has either evolved beyond recognition or, disappeared entirely. In about 40,000 years, Voyager will make its closest approach to Gliese 445, a red dwarf star, passing within about 1.6 light-years. It's kind of like a celestial handshake across the vastness of space. The golden record attached to Voyager carries sounds, music, greetings in 55 languages, and 116 images from Earth, all engineered to survive over 1 billion years in the harsh environment of space. This makes Voyager not just a scientific instrument, but possibly the most enduring monument humanity will ever create, carrying the essence of our species into the cosmic deep, long after Earth's continents have shifted beyond recognition.
The real discovery.
The most profound revelation from Voyager 1's journey isn't about discovering aliens or wormholes. It's really about understanding that interstellar space is a dynamic, structured environment all its own, with weather patterns, magnetic topography, and radiation zones. The spacecraft revealed that our solar system exists within a kind of protected oasis, with the sun's heliosphere shielding us from an environment that's way more intense and radiation-filled than anyone realized. The transition to interstellar space isn't simple, it's messy and complex, with magnetic fields that don't line up the way we expected, and plasma waves that show constant activity. The interstellar medium has layers, fronts and boundaries that shape the invisible architecture of our galaxy. Most importantly, Voyager showed us that we live in a cosmic shelter. Our solar system isn't just our home, it's really our sanctuary in a galactic storm raging beyond our protective bubble, making Earth even more precious than we ever imagined. So there you have it. Voyager 1 didn't just reach the other side, it discovered that the other side is nothing like we expected. Which part surprised you the most about interstellar space? Let me know in the comments below. If you enjoyed learning about humanity's greatest space exploration achievement, make sure to like this video, share it with someone who loves real science as much as you do, and don't forget to subscribe to Sci and Y for more mind-blowing discoveries about our incredible universe. Until next time, keep questioning and keep exploring. Interstellar space begins where the sun's influence fades, and the solar wind finally yields to the raw plasma of the Milky Way. Since 2017 we have confirmed just 3 visitors from that vast realm: the puzzling Oumuamua, herald of surprises, volatile comet Borisov, and now the outsized newcomer 3I Atlas. Each object is a priceless sample return mission delivered for free by nature, letting us probe chemistry, structure and age far beyond the planets. Tonight we collect every solid fact astronomers have pieced together about this latest cosmic ambassador. Beyond the heliopause, our interstellar visitors. The solar system's frontier is the heliopause, a shifting magnetic shell standing roughly 18 billion kilometers from the Sun. When Voyager 1 pierced that frontier in 2012, its plasma detector confirmed the long-predicted transition into interstellar space. Densities jumped, solar origin particles vanished, and cosmic ray counts spiked. Since then, terrestrial telescopes have reverse experienced the same crossing by spotting travelers arriving from the galaxy's dark sea. The odds are daunting. Dynamical models suggest only a few hundred-meter-scale bodies wander through the inner solar system each century. Yet modern wide-field surveys and continuous sky patrols have already netted 3 confirmed interstellar objects in just 8 years. Their hyperbolic speeds, inbound directions, and inability to be captured by solar gravity reveal origins that lie light-years away. Each new detection is therefore a planetary science windfall, a primitive shard of another star's debris disk, altered by eons of irradiation and micrometeoroid pummeling, finally falling within reach of Earth's spectrographs. As instrumental sensitivity grows, researchers expect a steady trickle of similar emissaries, gradually transforming Exotica into a statistically rich field of comparative planetology. The third visitor, 3I/ATLAS discovery. On June 2025, the twin Schmidt telescopes of the Asteroid Terrestrial Impact Last Alert System swept across the pre-dawn sky and registered an object moving too fast to be bound to the Sun. Alert messages flashed from Hawaii to South Africa and onto the Minor Planet Center, where the trajectory was confirmed within hours. Principal investigator Dr. Larry Deneau announced the team had netted 3Y Atlas, humanity's 3rd verified interstellar wanderer. Early photometry implied a remarkable diameter between 10 and 20 kilometers, at least an order of magnitude larger than Oumuamua. That sheer size promised ample reflected sunlight for spectroscopy, galvanizing observatories on 5 continents to obtain time-critical data. Infrared spectra hinted at complex organics, millimeter-wave receivers searched for exotic volatiles, radar attempted shape reconstruction when geometry allowed. The discovery also demonstrated how automated pipelines, artificial intelligence vetting, and instantaneous worldwide coordination can turn a few faint pixels into an unprecedented international campaign within a single rotation of Earth. 3Y Atlas thus became both a scientific target and a systems engineering triumph, showing that planetary defense infrastructure doubles as an accidental interstellar object early warning net. A hyperbolic journey at 58 kilometers. Trajectory solutions from JPL's Horizon system reveal 3I Atlas, racing along a hyperbolic trajectory with an inbound heliocentric speed of 58 kilometers per second. Calculations by Dr. Davide Farnochia show the path threads the orbits of Mars and Jupiter before the object slingshots back toward the galactic northwest, never to return. That excess velocity, nearly 3 times Earth's orbital speed, guarantees the visitor is unbound. No realistic gravitational interaction could capture it. Dynamical backtracing suggests 3Y Atlas last crossed the galactic plane 30 million years ago, and may have originated near the Carina Sagittarius spiral arm. though stellar encounter uncertainties are large. During its brief stay, it will feel weak but measurable tugs from planetary masses, allowing researchers to test N-body propagation codes under extreme boundary conditions. The rapid passage also forces astronomers into a sprint. Every observing window must be filled, sometimes with instruments never before aimed at the same target in a single night. Lessons learned from these coordination drills will feed directly into mission concepts such as ESA's Comet Interceptor, designed to launch quickly toward the next unpredictable celestial visitor. Brightness, rotation, and the 29-hour cycle. Time series photometry from the Nordic Optical Telescope reveals these quasi-periodic brightness swings of about 9/10 of a magnitude. This maps onto a rotation period of, well, around 29 hours. Data from the European Southern Observatory confirm an irregular, likely elongated body. Its long axis could exceed 9 kilometers, which is quite something. Now, if we invert the light curve, it suggests an axis ratio of approximately 3:1. This is comparable to Oumuamua's extreme proportions but on a much grander scale. The stability of this amplitude argues against the idea of loose rubble. Instead, it seems that 3I/Atlas might possess a cohesive monolithic core. This core is likely overlain by mantling regolith that accumulated during its galactic journey. Surface scattering models propose alternating patches of dark carbonized crust and brighter, possibly icy facets. These rotate into sunlight, driving the observed flux pattern. Continued monitoring aims to detect Yorp-induced spin-up or subtle precession. These phenomena could reveal internal density gradients. Polarimetric measurements planned for perihelion will test whether charged particle implantation or interstellar UV processing has glassified surface grains, a state never observed on indigenous comets. So, every rotational cycle opens a time-lapse window onto geological processes, operating far beyond the reach of any spacecraft. Coma, tail, and cometary activity. Solar heating at 1.5 astronomical units would normally trigger vigorous sublimation in an ice-rich nucleus. Yet, the Spitzer Space Telescope detected only a whisper of carbon monoxide and carbon dioxide. Lead investigator Dr. Colin Snodgrass suggests that cosmic ray gardening over millions of years may have sintered 3I/Atlas's upper meters into an insulating crust. This crust throttles volatile escape. Ground-based narrowband filters isolate a tenuous cyanogen halo, but production rates are nearly 2 orders of magnitude below those of Comet Borisov at a comparable distance. Radar attempts from Goldstone found no large dust grains, which is consistent with a surface depleted in friable material. The resulting weak coma and filamentary tail defy classical comet models. This suggests either an unusual primordial composition or extreme evolutionary processing. Should deeper layers ever fracture, a sudden jet could alter the trajectory. This would offer a real-time test of non-gravitational forces on an interstellar scale. Monitoring continues around the clock because even a modest outburst would provide precious gas for isotopic assays. This could potentially distinguish whether the body formed around a metal-poor population 2 star or within a young planet-forming disk more like our own nebular cradle. Oumuamua versus Borisov versus 3I/Atlas. Comparative planetology now has 3 data points beyond the heliopause. Oumuamua, flagged in 2017, was a cigar-shaped 200-meter object. It had perplexing non-gravitational acceleration but no detectable gas. Borisov erupted in 2019 with classical dust jets rich in carbon monoxide and hydrogen cyanide. It behaved like a solar system comet transplanted intact. In contrast, 3I/Atlas is 10 times larger than Oumuamua. It shows Borisov-style composition signatures only faintly and rotates slowly. Together, they outline a spectrum of possibilities: dormant shard, pristine comet, and massive, highly processed giant. Spectral slopes vary from Oumuamua's red, organic-rich hue to Borisov's more neutral tones. 3I/Atlas sits in between, pointing to mixed ice rock interiors masked by millennia of irradiation. Dynamically, all 3 arrived on different galactic vectors, indicating no shared parent system. The trio's collective diversity is reshaping models of planetesimal ejection. This implies that every maturing planetary system may fling out thousands of distinct fragments, icy, rocky, or hybrid, into interstellar exile. Future detections by Rubin Observatory will determine whether our current sample is typical or a statistical fluke driven by small number bias and selection effects. A 3 billion 11-year-old traveler. Isotope ratio modeling and cosmic ray exposure calculations, bracket 3 I Atlas's formation epoch between 3 and 11 billion years, actually predating the Sun at the upper bound. High-energy proton bombardment gradually converts surface ice to complex refractory organics, which leads to the dark, reddish spectra seen in long-aged Kuiper Belt objects, and similar signatures adorn our visitor. Laboratory analogs produced under accelerator beams match the object's infrared absorption bands, supporting an ancient surface residency in the galactic field. Queen's University Belfast researcher Dr. Alan Fitzsimmons notes anomalously low crystalline ice features, implying the body spent little time near its natal star before ejection. Over giga-years, random supernova shocks, molecular cloud passages, and gravitational nudges from passing stars sculpted its current orbit, effectively sandblasting volatile layers while leaving mineral matrices intact. Each detected molecule, therefore, archives conditions from epochs otherwise inaccessible to observation. Studying such relics refines timelines for disk evolution, migration, and dynamical instability in alien solar systems. With only 3 interstellar samples so far, every additional chemical clue counts exponentially toward mapping the history of matter across the Milky Way. October 30th, perihelion and beyond. On October 30th, 2025, 3 I/Atlas skimmed within just over 1 astronomical unit of the Sun, a geometry that placed it high in the northern skies. The James Webb Space Telescope devoted emergency directors discretionary time to obtain mid-infrared spectra, capturing silicate emission features rarely obtainable for interstellar bodies. Coordinated campaigns linked Subaru's visible light spectrograph, ALMA's sub-millimeter receivers, and amateur CCD networks into a single global array. The perihelion distance of 1.1 astronomical units allowed measurement of thermal inertia by tracking flux changes over the 29-hour rotation, constraining surface conductivity and porosity. Lead organizer Dr. Casey Lisi reports negligible change in gas production rates pre- and post-perihelion, bolstering the processed crust hypothesis. Hubble imaging after the closest approach detected a faint meteoroid trail, suggesting low-level dust loss perhaps triggered by microfractures. Precise astrometry during solar conjunction refined mass estimates via non-gravitational drift constraints, yielding a bulk density around 1.8 grams per cubic centimeter, denser than comet nuclei but lighter than stony asteroids. As 3 I/Atlas recedes, radar pings and thermal mapping will continue until signal-to-noise evaporates, freezing an irreplaceable dataset for decades of post-mission analysis. Future observations and scientific opportunities. The forthcoming Vera C. Rubin Observatory promises to transform fleeting luck into routine science, with its legacy survey of space and time projected to discover dozens annually of interstellar objects as faint as 24th magnitude. Pipeline architect Dr. Michelle Bannister is configuring machine learning classifiers to flag hyperbolic motion within hours, enabling rapid response spectroscopic triage. Complementary radio searches at FAST and Meerkat will probe for OH masers produced when unprocessed ices meet sunlight, while ESA's proposed Comet Interceptor could be retargeted to chase the next sizable wanderer. Astrodynamicists are refining solar sail trajectories capable of 5 astronomical units per year departures, potentially intercepting outbound objects for close-up imaging or sample capture. Coupled with isotope microanalysis, such missions would revolutionize understanding of galactic chemical gradients, delivering ground truth unattainable by remote sensing alone. Moreover, interstellar grains embedded in Earth's atmosphere, first cataloged by NASA's Stardust mission, could be chemically matched to parent bodies like 3 I/Atlas, linking macroscopic dynamics with microscopic composition. These interdisciplinary strategies will crystallize a new subfield, galactic small-body science, uniting astronomy, planetary geology, and heliophysics under a single question: how does matter move, evolve, and mingle across star systems? Conclusion and cosmic perspectives. In a single decade, humanity has advanced from 0 confirmed extrasolar planetesimals to detailed dossiers on 3, culminating in the colossal Robert Werik discovery lineage that now includes 3 I/Atlas. Each arrival widens our chemical dictionary, tests dynamical models, and reminds us the solar system is porous, not isolated. The study of interstellar visitors transforms accidental alignments into deliberate natural experiments, revealing chemical signatures forged under alien suns. Ultimately, these bodies invite a profound, humbling realization. Planet formation, collision, and ejection are universal, scattering shards of distant worlds throughout the galaxy. As surveys grow sharper and propulsion methods bolder, future scientists will map these shards into a web of shared origins, dissolving the parochial notion that samples must be fetched by billion-dollar probes. Instead, the galaxy occasionally mails postcards in the form of ancient rocks, carrying isotopic clues and perhaps organic seeds. Harvesting their stories will redefine planetary science from a solar system discipline into a truly galactic understanding, linking every world, seen or unseen, into a dynamic, ever-exchanging community of matter. 3I/Atlas is already dimming, yet its data trove will inspire research for years. Whether colossal comet, irradiated asteroid, or something even stranger, it confirms our cosmos is alive with wanderers older than Earth itself. Which mystery intrigues you most? Its muted coma, ancient chemistry, or breakneck speed? Let us know in the comments. Like, share, and subscribe to Sci and Y for more journeys beyond the heliopause. Until next time, keep looking up and stay curious.
Welcome to Sci and Y, where we decode the mysteries of our universe through rigorous scientific analysis. Today, we're investigating the enigmatic interstellar visitors that have astronomers worldwide questioning everything we thought we knew. From the puzzling Oumuamua to the massive newcomer 3I Atlas, these cosmic wanderers challenge our understanding of what's possible in the vast expanse of space. Join us as we explore the data, examine the theories, and ask the fundamental question, are we alone? Oumuamua Discovery and Anomalies. In October 2017, the Pan-STARRS survey in Hawaii detected something unprecedented: Oumuamua, the first confirmed visitor from another star system. This elongated object, measuring approximately 800 meters in length with an extreme 10:1 aspect ratio, defied all known classifications of celestial bodies. What truly baffled scientists was its unexplained acceleration away from the Sun without any detectable cometary outgassing or tail formation. Traditional physics couldn't account for this behavior, leading to intense scientific debate. Harvard astrophysicist Avi Loeb proposed the controversial hypothesis that Oumuamua might be an artificial light sail constructed by extraterrestrial intelligence. Other researchers suggested more conventional explanations, including exotic compositions like hydrogen or nitrogen icebergs. However, each natural explanation faced significant challenges when confronted with observational data. The object's discovery fundamentally altered our approach to studying interstellar space, revealing that the void between stars isn't as empty as previously believed. Despite extensive analysis using multiple space and ground-based telescopes, Oumuamua's true nature remains one of astronomy's greatest mysteries. UFO and UAP encounters and theories. The scientific community has increasingly focused on unidentified aerial phenomena following credible reports from U.S. Navy personnel. The most documented case was in 2004, an encounter with the infamous Tic Tac object off California's coast. This white, featureless craft demonstrated flight characteristics that violate known aerodynamic principles, including instantaneous acceleration and seemingly impossible maneuvers. Multiple radar systems tracked the object simultaneously while trained pilots provided visual confirmation. Some researchers have proposed advanced theories to explain these phenomena, including plasma-based holographic projections or exotic propulsion technologies. The physics of such systems would require manipulation of electromagnetic fields on scales currently beyond human capability. Government acknowledgement of retrieved crashed objects has added credibility to these reports, with intelligence sources confirming multiple recoveries. The correlation between increased UAP sightings and humanity's growing space-based observation capabilities raises intriguing questions about potential monitoring activities. Advanced civilizations might employ sophisticated surveillance technologies to assess emerging technological species without direct contact. Bob Lazar analysis. Bob Lazar's claims about reverse-engineered extraterrestrial technology at Area 51 have influenced UFO research for decades, despite ongoing scientific skepticism. His detailed descriptions of anti-gravity propulsion systems powered by element 115 seemed purely fictional in the 1980s, yet this super-heavy element was successfully synthesized in laboratories in 2003. Lazar described witnessing craft that manipulated gravitational fields through bombardment of element 115 with protons, creating localized distortions in spacetime. While his educational credentials remain unverifiable and security clearance claims are disputed, some aspects of his technical descriptions align with emerging theoretical physics concepts. The Alcubierre warp drive equations, published after Lazar's claims, describe similar spacetime manipulation techniques for faster-than-light travel. Modern physics recognizes that gravity is indeed a manifestation of curved spacetime, making field manipulation theoretically possible with sufficient energy control. However, the energy requirements for such technologies would exceed current human capabilities by orders of magnitude. Lazar's influence on UFO culture persists because his descriptions aren't entirely inconsistent with advanced theoretical physics. Light sail hypothesis. Professor Avi Loeb's revolutionary light sail hypothesis represents a paradigm shift in how we interpret anomalous astronomical observations. His mathematical analysis demonstrates that radiation pressure from stellar light could account for Oumuamua's mysterious acceleration if the object possessed specific physical characteristics. For photon pressure to explain the observed forces, the object would need to be extremely thin, less than a millimeter, while maintaining structural integrity across interstellar distances. This requires materials with strength-to-weight ratios far exceeding natural substances, suggesting advanced engineering. Loeb's calculations show that such a sail could maintain stable flight patterns across vast cosmic distances, making interstellar travel feasible for sufficiently advanced civilizations. The hypothesis gained attention because it elegantly resolves the contradiction between Oumuamua's acceleration and lack of visible outgassing. Critics argue that natural explanations involving exotic ices remain more probable, but Loeb maintains that scientific objectivity demands consideration of all possibilities. His work has reinvigorated the search for extraterrestrial intelligence by demonstrating how conventional astronomical surveys might detect technological signatures from advanced civilizations. 3I Atlas, the new discovery. The discovery of 3I Atlas in early 2025 by the Asteroid Terrestrial Impact Last Alert System has sent shockwaves through the astronomical community. Initial observations suggest this interstellar visitor measures between 10 to 20 kilometers in diameter, making it potentially 200 times larger than Oumuamua, a size disparity that challenges statistical models of interstellar object populations. The object's velocity exceeds 60 kilometers per second, confirming its extrasolar origin through hyperbolic trajectory analysis. What makes 3I Atlas particularly intriguing is its unusual brightness and spectroscopic signatures suggesting metallic surface composition inconsistent with typical asteroids or comets. NASA's James Webb Space Telescope has detected infrared emissions indicating possible thermal management systems and structured materials. Unlike natural objects that should tumble chaotically through space, 3I Atlas appears to maintain stable orientation and controlled energy output. The statistical probability of discovering such a massive interstellar object as only our third detection approaches astronomical improbability. Advanced spectroscopic analysis reveals isotopic ratios unlike any solar system materials, supporting theories of formation in drastically different stellar environments. Atlas Telescope System. The Atlas network represents a revolution in automated astronomical surveys, utilizing 4 strategically positioned telescopes across Hawaii, Chile, and South Africa to monitor the entire visible sky. Each telescope, despite its modest 0.5-meter aperture, employs cutting-edge CCD arrays and sophisticated software algorithms capable of detecting objects moving against the stellar background. The system's strength lies in its temporal resolution. Scanning the complete sky every 24 hours enables detection of extremely fast-moving objects that traditional surveys would miss. Atlas technology, developed through collaboration between the University of Hawaii and NASA's Planetary Defense Coordination Office, processes millions of astronomical images using machine learning algorithms trained to identify anomalous motion patterns. The detection of 3I Atlas demonstrates the system's capability to catch interstellar visitors early in their solar system transit, providing crucial observation time before they disappear into deep space. Real-time data processing flags suspicious objects within hours of detection, triggering follow-up observations from major observatories worldwide. This automated approach has transformed asteroid detection from periodic manual surveys to continuous automated monitoring. Scientific theories and debates. The scientific community remains fractured over explanations for 3I Atlas's anomalous properties, with competing hypotheses attempting to reconcile observational data with known physics. The hydrogen iceberg theory proposes the object consists of solid hydrogen formed in the frigid depths of interstellar space, though this model struggles to explain structural stability over millions of years. Alternative nitrogen sublimation models suggest composition similar to Pluto's surface, potentially explaining observed outgassing without visible tail formation. Dr. Alan Fitzsimmons leads the natural origin camp, emphasizing the need for comprehensive spectroscopic data before considering exotic explanations. Conversely, advocates for expanded theoretical frameworks that might accommodate artificial construction scenarios. The fundamental problem remains the inconsistency between observed acceleration patterns and minimal detectable volatile emission, a contradiction that challenges basic cometary physics. Statistical analysis reveals the probability of discovering such a large object through random interstellar encounters approaches negligible values, forcing scientists to question either our understanding of object size distributions or the randomness of these visits. Future detection technology. The Vera C. Rubin Observatory in Chile represents the next generation of astronomical detection systems, featuring an unprecedented 8.4-meter primary mirror coupled with the world's largest digital camera. This technological marvel captures images spanning 40 full moons per exposure while maintaining resolution sufficient to detect objects smaller than previous generation surveys. The Legacy Survey of Space and Time will systematically photograph the southern sky every few nights for a decade, creating a comprehensive temporal database of cosmic changes. Advanced machine learning algorithms process this massive data stream in real time, identifying asteroids, transient events, and anomalous objects within hours of observation. The system's enhanced sensitivity will enable detection of interstellar visitors when they're still months or years from closest approach, providing unprecedented preparation time for detailed study campaigns. Rubin's statistical power promises to resolve fundamental questions about interstellar object populations by discovering dozens of new visitors annually rather than the current rate of one every few years. This technology will either confirm that objects like 3I Atlas represent statistical outliers or reveal a previously hidden population. Theoretical implications. The implications of discovering objects like 3I Atlas extend far beyond astronomy into fundamental questions about intelligence in the universe. SETI researchers are developing protocols for analyzing these visitors' behavior patterns for signatures of intentional control or embedded communications. The concept of galactic probe networks gains credibility when considering the efficiency of automated exploration versus biological travel across interstellar distances. Advanced civilizations might deploy self-replicating surveillance systems throughout the galaxy, monitoring emerging technological species while maintaining strategic distance. Theoretical models suggest such networks could map entire galactic regions over millions of years, creating comprehensive databases of planetary development. The timing correlation between humanity's space-age emergence and increased interstellar visitor detection rates raises intriguing questions about causation versus coincidence. Cosmic archaeology theories propose that evidence of ancient civilizations might be found in the form of derelict probes or monitoring stations throughout our galactic neighborhood. These discoveries force reconsideration of humanity's cosmic significance. We may not be isolated observers but subjects of ongoing study by intelligences that achieved technological maturity eons before our species emerged. Future endeavors. The European Space Agency's Comet Interceptor mission represents humanity's first attempt at planned rendezvous with an interstellar visitor, utilizing advanced trajectory prediction and rapid deployment capabilities. International coordination between ground-based observatories and space-based assets is evolving toward real-time global response networks capable of comprehensive data collection from future encounters. NASA's proposed rapid response spacecraft concepts could launch within months of detecting new visitors, using ion propulsion and gravitational assists to achieve intercept trajectories before objects exit our solar system. Project Lyra, designed to pursue Oumuamua, demonstrates the technical feasibility of interstellar chase missions using current technology and careful orbital mechanics. Advanced sample return capabilities would enable direct analysis of interstellar materials, potentially revealing formation conditions in alien star systems or evidence of artificial construction. Future missions will deploy sophisticated spectrometers, mass analyzers, and imaging systems capable of determining composition, structure, and origin with unprecedented precision. These endeavors mark humanity's transition from passive observation to active exploration of interstellar phenomena, potentially yielding definitive answers about the nature of these mysterious visitors. The scientific investigation of interstellar visitors like 3I Atlas continues to challenge our understanding of the cosmos and our place within it. As detection technology advances and analytical methods improve, we stand on the threshold of potentially revolutionary discoveries about our galactic neighborhood. Whether these objects represent exotic natural phenomena or evidence of cosmic intelligence, they've already transformed how we approach the study of our universe. The data keeps coming, and the questions keep getting more profound. Keep exploring with Sci and Y as we decode the mysteries that surround us and push the boundaries of human knowledge into the unknown.
On September 26, 2022, NASA achieved something truly unprecedented. They deliberately crashed a spacecraft into an asteroid at 6.6 kilometers per second and, get this, completely changed its orbit. The DART mission wasn't just about proving we could hit a space rock. No, it was humanity's first successful test of planetary defense technology. But what happened after the collision honestly shocked scientists and revealed truths about asteroids that nobody really expected. The aftermath of this cosmic collision is rewriting everything we thought we knew about protecting Earth from space threats. The journey to impact. NASA's Double Asteroid Redirection Test, or DART, began its historic journey on November 24, 2021, launching from Cape Canaveral Space Launch Complex 40 atop a SpaceX Falcon 9 rocket. The refrigerator-sized spacecraft traveled for nearly 10 months across 11 million kilometers of space to reach its target, a small asteroid moonlet called Dimorphos. The mission team, led by project scientist Dr. Nancy Chabot at the Johns Hopkins Applied Physics Laboratory, had meticulously planned every detail of this unprecedented experiment. Unlike previous space missions that aimed to study celestial objects, DART was designed with one purpose: to slam into Dimorphos and change its orbital path around the larger asteroid Didymos. The spacecraft carried advanced navigation systems that would allow it to autonomously guide itself to impact during the final 4 hours of flight, since the 11-minute communication delay with Earth made real-time control totally impossible. As DART approached its target, onboard cameras captured dramatic images of the asteroid growing larger and larger, marking humanity's first intentional collision with another world for planetary defense purposes.
The perfect target.
Dimorphos proved to be the ideal testing ground for this groundbreaking experiment, measuring approximately 160 meters in diameter and orbiting its larger companion Didymos every 11.9 hours. The binary asteroid system, located about 11 million kilometers from Earth at the time of impact, posed no threat to our planet, making it a safe target for this high-stakes test. Didymos, the larger asteroid measuring 780 meters across, served as the gravitational anchor for its smaller moonlet. Scientists chose this system because any change in Dimorphos's orbit could be precisely measured from Earth using ground-based telescopes and radar systems. The asteroid pair was discovered in 1996 and had been extensively studied, providing researchers with detailed baseline measurements of their orbital characteristics. The proximity of the two asteroids meant that even a small change in Dimorphos's velocity would produce a measurable shift in its orbital period around Didymos. This binary system represented the perfect natural laboratory for testing kinetic impactor technology, close enough to Earth for accurate observation, large enough to produce detectable changes, yet far enough away to ensure complete safety for our planet throughout the experiment. The moment of impact. At exactly 23:14 UTC on September 26, 2022, DART slammed into Dimorphos at a closing speed of 6.14 kilometers per second, releasing kinetic energy equivalent to approximately 2.5 tons of TNT. The collision occurred with pinpoint accuracy, striking the asteroid's surface and instantly vaporizing the 610-kilogram spacecraft along with a portion of the asteroid's rocky material. Ground-based telescopes around the world captured the dramatic moment as a brilliant flash of light erupted from the impact site, followed by an expanding cloud of debris that grew brighter over several hours. The Hubble Space Telescope and James Webb Space Telescope immediately began observing the aftermath, documenting the evolution of the ejecta plume as it stretched across thousands of kilometers of space. Within minutes of impact, the debris cloud had expanded beyond Dimorphos itself, creating a spectacular tail of material that resembled a comet's tail stretching behind the asteroid. Amateur astronomers joined professional observatories in tracking the collision's effects, witnessing history as humanity demonstrated its ability to alter the path of a celestial object. The impact created seismic waves that rippled across Dimorphos's surface, potentially reshaping the asteroid's internal structure in ways that scientists are still working to understand.
Beyond all expectations.
The results of the DART impact exceeded every prediction and shattered the mission's success criteria. Instead of the minimum 73-second change in orbital period that would have declared the test successful, Dimorphos's orbit around Didymos shortened by an astounding 32 minutes. This dramatic change represented a 26-fold improvement over the mission's baseline requirements, proving that kinetic impactor technology was far more effective than scientists had dared to hope. The massive orbital change resulted not just from the direct momentum transfer of the spacecraft's impact, but from the unexpected efficiency of the momentum multiplication effect created by the ejected debris. As material blasted away from the impact site, it carried additional momentum in the opposite direction, acting like a natural rocket engine that amplified the deflection effect. Dr. Tom Statler, DART program scientist at NASA, described the results as a watershed moment for planetary defense and humanity's ability to influence our cosmic environment. The orbital change was so significant that it could be measured by small telescopes and even confirmed by radar observations from Arecibo Observatory and the Goldstone Deep Space Communications Complex. This level of deflection meant that if Dimorphos had been on a collision course with Earth, the impact would have shifted its trajectory by hundreds of thousands of kilometers.
The mysterious ejecta cloud.
The debris cloud created by DART's impact revealed secrets about asteroid composition that puzzled scientists worldwide. Instead of the uniform dust plume that computer models predicted, the ejecta displayed complex structures including multiple debris streams, spiral patterns, and irregular particle distributions that suggested Dimorphos had a far more complex internal structure than anticipated. Dr. Christina Thomas at Northern Arizona University, who led the observational campaign, noted that the debris cloud evolved in unexpected ways over the following weeks. Some particles were ejected at speeds exceeding 500 meters per second, while others moved much more slowly, creating distinct populations of material with different trajectories and behaviors. The cloud's asymmetric shape indicated that Dimorphos wasn't a solid uniform rock, but likely a rubble pile, a loose collection of smaller rocks and boulders held together by weak gravitational forces. High-resolution images from ground-based telescopes revealed that the ejecta contained both fine dust particles and larger chunks of material, some potentially meters in size. The debris cloud's brightness variations suggested that different types of material were being ejected from various depths within the asteroid, providing unprecedented insights into the internal layering and composition of small solar system bodies.
Hera's investigative mission.
Recognizing the need to understand DART's impact in detail, the European Space Agency launched the Hera mission in October 2024 to conduct a comprehensive post-impact investigation. This follow-up mission represents an unprecedented example of international cooperation in planetary defense, with Hera scheduled to arrive at the Didymos system in late 2026 to examine the crater left by DART's collision. The spacecraft carries advanced instruments including high-resolution cameras, thermal imagers, and radar subsystems designed to map both asteroids down to centimeter-scale resolution. Hera will measure the precise size and depth of DART's impact crater, analyze the composition of exposed subsurface material, and determine how the impact altered the internal structure of both Dimorphos and its parent asteroid Didymos. The mission will also deploy two small CubeSats called Juventus and Milani to conduct complementary investigations, including the first radar sounding of an asteroid's interior and detailed gravitational field mapping. Dr. Patrick Michel, Hera's principal investigator, emphasized that understanding the physical properties revealed by DART's impact is crucial for designing future deflection missions. The data collected by Hera will validate computer models used to predict deflection effectiveness and provide the foundation for operational planetary defense systems.
Unraveling asteroid mysteries.
The DART impact revealed that small asteroids like Dimorphos are far more complex than scientists previously understood, fundamentally changing how we think about these cosmic building blocks. Pre-impact models assumed asteroids were relatively simple objects with predictable responses to external forces, but the dramatic success of the deflection demonstrated that rubble pile asteroids behave more like fluid structures than solid rocks. Dr. Andy Rivkin at the Johns Hopkins Applied Physics Laboratory noted that the impact's efficiency suggested Dimorphos has very low internal cohesion, allowing the impact energy to propagate throughout the entire structure and eject material from multiple locations. The asteroid's surface appears to be covered in loose regolith, fine, rocky debris accumulated over millions of years that was easily disturbed by the impact's shock waves. Spectroscopic observations of the ejecta revealed that Dimorphos contains ordinary chondrite minerals, similar to the most common meteorites found on Earth, but with unusual proportions that suggest a complex formation history. The impact also provided insights into how small asteroids respond to tidal forces from their parent bodies, with evidence suggesting that Dimorphos experiences ongoing surface changes due to its proximity to Didymos. These discoveries have profound implications for understanding asteroid evolution, the formation of binary systems, and the potential resources available on near-Earth asteroids for future space missions.
Complications for future defense.
While DART proved that kinetic impactors can deflect asteroids, the mission also revealed complications that will influence future planetary defense strategies. The unexpectedly large orbital change, while impressive, highlighted just how difficult it is to predict exactly how different asteroids will respond to impact. Dr. Nancy Chabot emphasized that the momentum multiplication factor, the ratio of total momentum change to the spacecraft's initial momentum, varied significantly from pre-impact predictions, reaching values between 2.2 and 4.9 depending on the measurement method. This variability means that future deflection missions will require detailed advanced characterization of target asteroids to predict their response accurately. The complex ejecta pattern suggested that asteroid internal structure, surface composition, and rotation state all influence deflection efficiency in ways that current models just don't fully capture. The discovery that small asteroids behave more like loosely bound rubble piles than solid objects means that deflection strategies must account for potentially dramatic differences in material properties between different asteroid types. Mission planners now recognize that successful planetary defense will require a library of deflection techniques tailored to specific asteroid characteristics, rather than a one-size-fits-all approach. The DART results also emphasize the importance of early detection and characterization, since deflection effectiveness depends critically on understanding an asteroid's physical properties years before any potential impact threat.
Global Planetary Defense Initiative.
The success of the DART mission has catalyzed unprecedented international cooperation in planetary defense, transforming what was once considered science fiction into practical space policy. NASA's Planetary Defense Coordination Office, established in 2016, now works closely with the European Space Agency, Japan's JAXA, and other international partners to develop comprehensive strategies for detecting and deflecting hazardous near-Earth objects. The United Nations Office for Outer Space Affairs has established new protocols for sharing asteroid tracking data and coordinating deflection missions, recognizing that planetary defense is a global responsibility requiring multinational collaboration. Ground-based survey telescopes like the Catalina Sky Survey in Arizona and the Linear program in New Mexico continue discovering new potentially hazardous asteroids at rates exceeding 1,000 per year, building a comprehensive catalog of objects that might someday threaten Earth. Space-based detection systems, including NASA's NEOWISE mission and the planned NEO Surveyor telescope, will dramatically improve our ability to find and track smaller asteroids that ground-based systems might miss. The establishment of the International Asteroid Warning Network ensures that discovery data reaches decision-makers quickly enough to enable deflection missions if needed. These coordinated efforts represent humanity's first serious attempt to protect our planet from cosmic threats that have caused mass extinctions throughout Earth's history. The future of planetary defense. The DART mission's spectacular success has laid the foundation for humanity's first operational planetary defense system, but it also revealed how much we still need to learn about deflecting dangerous asteroids. Future missions will build on DART's legacy by testing different deflection techniques including gravity tractors, nuclear standoff detonations, and enhanced kinetic impactors designed for specific asteroid types and threat scenarios. NASA's follow-up missions are already in development, including concepts for multi-spacecraft deflection systems that could handle larger asteroids or provide backup capabilities for critical deflection attempts. The double asteroid redirection test proved that humanity possesses the technological capability to alter the course of celestial objects, marking our species' transition from passive observers of cosmic events to active participants in shaping our solar system's dynamics. Advanced computer simulations now incorporate DART's impact data to model deflection scenarios with unprecedented accuracy. enabling mission planners to design precise interventions for specific threat asteroids. The mission's success has also sparked development of rapid response deflection technologies that could be deployed on shorter timescales for newly discovered threats. Most importantly, DART demonstrated that international cooperation and scientific expertise can overcome seemingly impossible challenges, providing a template for tackling other global threats that require coordinated human action on planetary scales. So there you have it. NASA didn't just hit an asteroid, they revolutionized planetary defense and revealed that asteroids are far stranger than we imagined. Which discovery about the DART mission surprised you the most? Let me know in the comments below. If you enjoyed learning about humanity's first successful planetary defense test, make sure to like this video, share it with someone who loves real space breakthroughs, and don't forget to subscribe to Sci and Y for more incredible discoveries about our universe. Until next time, keep exploring the cosmos.